Hi there, my name is Emmy and I'll be your guide for the second module of Day 6. I'll be talking to you about the applications of second derivative. Please pause this presentation at any time when you need more time to think about something. In the previous module, we learned that one of the steps to find the point of inflection is to set the second derivative to 0. We also learned how the second derivative can be used to determine the nature of the stationary points. These are helpful when it comes to sketching functions. Remember that if the second derivative is positive on an interval, then the function is concave up over that interval. Let's say that there is a stationary point at P. Then if the second derivative at P is positive, then the function has a local minimum at P. Similarly, if the second derivative is negative on an interval, then the function is concave down over that interval. Let's again say that there is a stationary point at P. Then, if the second derivative at P is negative, then the function has a local maximum at P. So to summarize, if the function with a stationary point at P has a positive second derivative at P, then the function has a local minimum at P. If the function with a stationary point at P has a negative second derivative at P, then the function has a local maximum at this point P. So what happens if the second derivative at the stationary point is 0? Well, then we cannot tell anything from the second derivative. In that case, we can determine the nature of the stationary point as we did in Day 5. That is, by finding the gradient of the curve at the left and right of the stationary point. Now, for example, let's consider sketching the curve y equals to x cubed minus 3x. First, find the stationary points. You are probably familiar with this step, but let me repeat again. To find the stationary points, differentiate the function, let it equal to 0, and solve for x. So here, stationary points are 1 and minus 2, and minus 1, 2. Next, we find the second derivative, which is 6x. We'll have the second derivative here again on this slide for your quick reference. Substitute the stationary point 1 minus 2 into the second derivative. This will give us 6. Since it is positive, the curve is concave up at this point, so 1 minus 2 is a local minimum. Substitute the other stationary point, minus 1, 2, into the second derivative. At this point, this second derivative is negative. So the curve is concave down here. Hence, minus 1, 2 is a local maximum. If we let the second derivative equal to 0, we get x equals to 0. This means that we have a possible point of inflection at x equals to 0. Remember, this is a possible point of inflection, which means it may not be a point of inflection. To test if it is a point of inflection, we check the second derivative of the left and right of that point. Here, if x is less than 0, it is easy to see the second derivative will be negative. If x is greater than 0, then clearly the second derivative is positive. So this means that concavity changes at x equals to 0. So there is a point of inflection at the origin. Remember, for every possible point of inflection, you will need to check the sign of the second derivative on the left and right of the possible point of inflection. If the signs do not change, then it is not a point of inflection. Now to sketch the curve y equals to x cubed minus 3x, plot the stationary points, and use your knowledge of the concavity of the curve determined from the second derivative to draw the curve. The resulting curve will look like what you see on this slide.